for the first panel that will be devoted to explainable AI from the concept to the real-world application. And our first speaker, Ronan, Hamon, I hope I pronounced it correctly. It's a scientific officer with the Joint Research Center at the European Commission located in Ispra, Italy. His current research interests focus on robustness, security, and explainability of machine learning, as well as on applications on cybersecurity and automated driving. So thank you, Ronan.
Thanks. Can I share the presentation? Okay, thank you. I hope everybody can hear me well. Good afternoon, everyone. So I'm Ronan Hamon. I'm working at the European Commission at the Joint Research Center. So I will talk mostly about some uses of explainable AI in not real context, but in more technical context. But before that, I would like to introduce the Joint Research Center, because I think so it makes sense. It helps to understand the context of this research. So the Joint Research Center is a Directorate General of the European Commission that, whose objectives is to provide independent, evidence-based knowledge and science to support European policies. So you know that the policy agenda on artificial intelligence at European level is quite important with, of course, the AI Act, but also other files like the liability of AI or standardization. And the GRC supports this activity and at the same time conducts research on relevant topics for which I'm concerned. I'm working on cybersecurity, robustness, and explainability. So I will not go into too much into details to present this explainable AI because we already had at least partially physically a discussion of what is explainable AI. So a set of techniques and methodologies to make humans understand the reasoning behind decision or predictions made by AI systems. And in practice, it is mostly machine learning models, because those are the type of techniques that are the biggest issue in terms of opacity. There is a taxonomy, a way to differentiate between different techniques, between interpretable models and post-hoc approaches. It was already been discussed, also global and local explanations. And those techniques applies either in black box or white box trainings, meaning that to compute the explanation, all the information might not be available. So the white box settings usually consider that there is access to the weights of the models, of the parameters, sometimes to the training set, to the parameters that we use to train the models, while a black box settings will be a case where there is only access to queries, for instance, to an API, and there is no access to the inner workings of the models. So this makes a big difference to what kind of explanation you can obtain. And also, I would like here to make a distinction between different types of black boxes. There is the black box by obfuscation, so you don't have access to data. And here, the way to solve this is to increase transparency. As has been discussed in previous talk, there is ways to provide information about models, about data, about processes. And XAI is not really about that. XAI is more to address opacity due to complexity. So to illustrate that, I will rely on some results we obtain in the context of a work on the interplay between explainable AI and the GDPR. And for this work, we consider two use cases, one on prediscovering, one on medical imaging, and to illustrate what kind of explanation. So the point was not to provide actual explanation. The model was actually not that informative, but to show what kind of modalities you can see for two types of models, one relying on tabular data and using classical machine learning like decision trees or non-forests, regression, which are very, not basic, but standard, at least pre-hype machine learning. And a second case on image classification using deep learning techniques, and in particular, convolutional neural networks. So a third use case could be now to add language modeling or generative image that will make use of even more advanced methodologies. But actually, the message I will try to convey in this presentation is that it's even reinforced by the current trend. And the trend we identified is actually a trend to higher complexity. We start from a situation where we had tabular data. That means set of data well structured with features hand-grafted by engineers or technicians, and with the meaning associated to each feature, to a set of techniques that rely on raw data like images or audio or any kind of data that have not structured easily identifiable. There is also a trend toward more complex models, from interpretable models like decision tree, where the logic is clearly visible in the structure of the model, a set of conditions, you follow the tree, and each time, depending on the value of the features, you go to one of the leaves that will tell you what is the outcomes of what is the prediction. Two models, like and mainly based on neural networks, where the prediction is given by many matrix multiplications, and the exact reasoning is completely hidden. There is also a trend to more complex algorithms, and here I show a typical life cycle of machine learning product that goes into data processing, to feature selection, to model training, model tuning, testing, deployment, and each of these steps involves a set of algorithms or processes that add complexity, that add obscurity in the full process, and that limits the understandability of the final outcomes. I will just discuss three main limitations of AI that have been identified. And I guess that will be also discussed in the second panel. The first one is the trade-off between accuracy and explainability. And the fact that those are two contradictory properties, and especially it is given in case in more and more complex tasks. The fact that machine learning models are designed to extract correlation, but not causal relationships. And what you obtain, what you uncover are correlations that may not be linked to actual causal phenomenon. And the third point is about the statistical uncertainty of XAI techniques themselves. Many techniques are based on actual statistical or machine learning principles and are then subject to accuracy, to reliability, lack of reliability, and also difficulty to interpret the explanation. So there is somehow an additional layer of complexity added by the XAI techniques themselves that requires some expertise to understand what is going on and to have a critical view on what outcomes the XAI techniques give to the user or the person who tries to make sense of the prediction of the model. I will illustrate that on the use case I described before. So the first one is an interpretable model, a decision tree. So I've explained you start from a root, and following depending on the value of the features you consider, you go either right or left, and you follow the tree like that. And one aspect of those interpretable models is that very quickly, what we call interpretable models tends to be not really interpretable. Here, this is a very simple case with a limited set of features, with only a depth of 5, which is rather small. And it is already quite hard to figure out what is the logic behind it. You can try to follow all the path, but there is already some difficulties. This is even increased when the size of the tree increases, and when you consider even not that complex techniques like Ronan forest, when you have this time multiple trees, you have multiple processes taking place to optimize over the tree. But this makes those interpretable models also quite challenging to interpret at the end. A second way to interpret, to give explanation for tabular data is to use feature importance techniques. Where here I use the Xabier that have been described, that's been mentioned in the previous talks. And this is basically putting a score to a feature, saying that, for instance, for the blue, this is for the decision tree, the variable, which is the net fraction of the revolving burden, has an importance of 0.5 compared to the other features. This is helpful and this is informative, but this is also subject to statistical uncertainty. And if you compare the different techniques, they seem to rely on different set of features. That will mean that there will be several ways to achieve sometimes even close results, but the features themselves is just a result of the optimization process, and it might not actually give a good picture of what the system is doing and what the person wants to achieve, what the developer, the provider wants to achieve when developing the systems. For medical imaging and image visualizations, I will not go too much into details, but you can visualize layers, which basically give you very little information, except that it seems to rely on some patterns that make sense, but in itself, it doesn't give a lot of information. A common way to achieve that is to make heat maps in front of images, and the red part giving regions that are not very important, that contribute negatively to the score, for instance, of malignancy, and the green one, positive contribution. But those methods are also subject to statistical accuracy. Here we can see that actually the model we are using is very bad because to detect pulmonary conditions, it is relying on bones, and which is actually not good. But this is not the point of the approach. Was not to develop a system to detect correctly, but to show that despite the fact that the model has a very high accuracy, it seems to rely on bad features. But you can actually compute different occlusion maps if you change the parameters. So those are very sensitive to variations. A last way would be to have some sort of counterfactual explanations and to show what kind of patterns you need to add to your image to switch from positive to negative, from negative to positive, and which is a bit in line with the counterfactual explanation I described before. So I will stop my presentation here. So the main message I would like to convey is first, on the state of the art from the technical point of view, Explainable AI is not able to provide minimal level explanation of AI systems for the limitations I've described. But at the same time, it is a great tool, and there's a lot of great advancement in the field. And it is a great tool to increase the transparency of AI systems, to make as part of other elements to increase transparency. And it also supports all the other requirements like robustness, human oversight that are in the ethical principles and are also in the legislation. So if you're interested a bit more on the last points, I would like just to point out an article that will be presented in 2 weeks, which is actually describing the role of explainable AI in the context of the AI Act, and which is a result of internal collaboration at the European Commission. Thank you very much.
Thank you. Thank you very much, Ronan.
Some technical support here. It's okay. We have the technical support from this. You want to move now to the next segment? Same way that we did. Stop working.
Do we have now? No? Can you tell us from the audience if you hear me? Hi? Okay, great. Thank you. Okay, then. Sorry for the technical issues. So now we will go to our second speaker of the first panel. Who is Joren Verspeurt. Joren, please. Joren Verspeurt, sorry, is currently working at Radix AI as a machine learning engineer and security officer responsible for data protection, focusing on the development of ethical and legally compliant AI solutions using natural language processing and time series methods for clients in the human resources and transport sectors. Thank you, Joren.
All right, good afternoon, everyone. My name is Joren. I work for a Belgian AI company called Radix, as Xabier already mentioned. I'm very pleased to be here. I am not a researcher. I'm not a policymaker. I'm an engineer. I build things. I'm also a security officer, which means that I try to keep our solutions compliant, among other things. And I'd like to give you a bit of background on the kind of projects we do at Radix. In particular, I'm going to highlight our job matching solution, our candidate intelligence platform named Talent API, and give you a bit of background on the kinds of considerations we took in designing it. All right. So to give you a bit of background about Radix, we make tailor-made AI services and solutions for all kinds of companies. We work in all kinds of different sectors as well. Transport, we work for the government, manufacturing, pharma, among other things. We've been making great strides in helping to do better agriculture with computer vision on satellite imagery, for example. We really believe in the idea of AI as a co-pilot, not as something that replaces decision-making, but something that augments the humans that use it. Our office is in Brussels, the main office, if you ever want to come visit us. All right, so the project I want to highlight is Talent API. It's technically a product that we sell. It's the only product we sell. What is it? It's what we call a candidate intelligence platform. I'll go a little bit more into what that means in a second. Just to give you some stats and figures, we have more than 1.5 million monthly active users, which for Belgium is quite a big deal. And we have seen through experiments with our clients that the recommendations that we give lead to, among other things, a 67% improvement in click-through rate, which is always a nice statistics for our clients. So what is the core of our product? We provide four-way matching. We recommend jobs to job seekers, candidates. We recommend those candidates to employers based on their CV and the description of the vacancy. We look for similar profiles if employer wants to find someone with similar skills to someone they already have employed, for example. And we also search for similar jobs to provide suggestions, for example, on a job platform. Now, what makes us unique? To answer that question, let me take you on a bit of a journey through time. This is particularly inspired by the journey we went through at our biggest client, and it involves the development of Talent API as it stands today. The system they used in the beginning, this client, is what we call narrow matching. It's based on business rules. It uses a fixed list of skills that they designed by committee. Someone sat down and listed all of the different skills that the system would know. If they have to update that standard, it takes approximately 5 years. I'm not exaggerating. This system works relatively well for the cases where it's deployed. But there are a couple of downsides. For example, it has bad support for incomplete profiles. If you haven't filled something in, it can't really help you, that specific attribute. It can't learn from feedback. It's a simple business rule system, so it has no learning components. And it also can't provide any personalized matching. It doesn't reason about your profile. It just looks at specific attributes of it and provides you matches based on that. What it is very transparent. It's fully documented. You can request this documentation. All of the logic behind it is very simple. And for any reasonable definition of explainability, it is explainable. You can look at the way that the rules work. You can look at the database behind it. It's very straightforward. But that's one key advantage that it does have. Now, in the beginning, we thought we might try, just as an experiment, to see whether a deep learning-based approach might work in this situation. Essentially, what we did was click prediction. We tried to predict whether someone would be interested in a particular vacancy. And we wanted to provide our client with something that's thought out of the box, that would give recommendations which, the classical narrow system would never give. Major advantage of this system was that it supported incomplete profiles. It was as configurable as the narrow matching system, and it could learn from feedback. We could train it to provide better suggestions. Unfortunately, it wasn't very transparent, and we had difficulties explaining its behavior, which wasn't great. And it also couldn't provide any personalized matches yet. So what is Talent API? It's kind of the best of both worlds. We work with an architecture that we call mini models, which I'll get back to, which provides us with a couple of nice benefits. We can still support incomplete profiles. The system is fully configurable by us or by the client. It learns from feedback because it has trainable components. And novel benefit, it can provide personalized matches based on past interactions. And also, most importantly, it's fair by design. We took great care in designing it to make sure that we don't have some of the negative points that some other more sophisticated AI solutions have. So to give you an idea of how our smart matching works and what some of the problems might be in providing matches, the main thing that we solve is that job seekers and employers use different terms for different skills. Might see, for example, Microsoft Excel written out in a job description, but it might be abbreviated to MS Excel or just Excel, or a misspelling of it or whatever in someone's CV. And a traditional matching engine, if it just looks at the plain text that it gets, wouldn't do very well with that. Also, job titles, descriptions are kind of a complex topic. You might see a vacancy for an administrative assistant. Someone might put on their resume that they have experience as a secretary. Again, a traditional system might not connect those two. So how do we solve it? We use natural language processing, a classical AI domain, to understand what people mean when they list specific skills, when they list job titles in their experience. We also have a cloud of linked skills so that we can inject some understanding of what skills are related to a specific skill that someone lists. I have a quick example here of what we mean when we say out-of-the-box suggestions. So we have a CV here on the left for an industrial baker, someone who works in a bakery as a QA inspector, who has worked in the past in food manufacturing. And the vacancy on the right side is for a construction site foreman, someone who works on construction sites, guaranteeing safety, maintaining materials, planning, that sort of thing. And as you can see, a traditional system would never suggest this vacancy for this person. Because none of the skills match, none of the interests that this person have match the pluses on the other side. Even simple things like the fact that this person prefers to work the night shift, that's seen as not compatible with the fact that the vacancy mentions that for this job, people work in shifts. What we can do is match the different elements of the CV in the vacancy. We go a little bit deeper. We see that, okay, if this person worked in manufacturing, they might be suited for work in construction. The fact that they were an inspector, that they worked with quality requirements, makes them a good fit for being a foreman. Yeah, there are a couple of more elements that match. So if you think about the design requirements for our system, we didn't want it to be a monolithic black box. We didn't want complex interactions like you see in other matching systems. For example, we saw the case of Amazon, I think it was, where their CV ranking system picked up on the fact that some candidates mentioned that they were part of the chess club, for example, and if they were in the chess club and they lived in a certain area, that must mean that they were from a higher socioeconomic background or something like that, and they would be a better fit for a management position or something. This is the type of interactions that we wanted to explicitly make impossible. Same with hidden proxies. The idea there is similar. We didn't want any proxy variables for things like gender. If someone mentions, I don't know, women's volleyball in their hobby, you could deduce that that person was a woman or identified as such, even though the CV doesn't list the gender explicitly. We also didn't want to go all the way back to the traditional system using the spaghetti of business rules. So what we came up with is an ensemble of simple specialized models which focus on one specific facet of a job match, and something that ranks based on weights which are configurable or trainable. The system works either way. I have a little illustration of how our scoring system works. I won't bore you with it, but it gives you a bit of an idea. So these mini models, they're not fixed parts of a whole that we sell the same way every time. As we see every day, one size does not fit all, so they can be picked and chosen depending on the situation. They can also be configured depending on the needs of the client. And typically, we configure them based on the target end users for our clients, specific compliance requirements that they have, and based on what we call the explainability budget. And that's a topic that I'll go a bit further into if you'll allow me. So I have here two different versions of one mini model. It's a very simple mini model. It's the location mini model. The left side is based on geo-coordinates. It just takes the difference between 2 points, the distance, and based on some criterion, it produces a score. Right? Simple function. That completely ignores whether it's actually feasible to travel from one place to another. On the right, we have a different mini model, which does take travel time into account. and which is a better representation of whether people can actually commute from these two, between these two places. This is a nice case where just adding some technological complexity provides better results without really compromising on explainability, even though you could argue that it's a bit less explainable, especially if you use, for example, a third-party service you don't have any access to provide these travel time numbers. This is a bit of a different scenario. See that my slide got a bit messed up. So this is two different alternatives for our skills mini model, which looks at the different skills that a candidate in a job present and ask for. The most basic version of this model just uses set intersection if vacancy asks for Google Sheets and, for example, the candidate mentions MS Excel. That doesn't overlap, won't get recognized, but it's a valid way of doing skill matching. It works well if all of the skills are standardized. Even in that scenario, you can get into situations where people don't list all of the implicit skills that they have, which would actually make them a better candidate for a specific job. So even in the scenario where you have fully standardized skills, it doesn't work that well. The model on the right is the one that we typically use in production. It's based on embeddings. So it's essentially the same kind of way of working as a typical language model. You take a piece of text, you turn it into some mathematical representation that you can reason with by computation. That captures the semantic information that we have in the skills and the titles. These things, and we can do a better job of matching the different skills to each other. But again, in this case, you might say that it's less explainable. It is based on a neural network model, even though, and you know, feel free to ask me about this afterwards. We have some provable characteristics of this model, and we have very good confidence in it. It is still, you know, more sophisticated machine learning that's slightly more black box than something like set intersection model. I won't go too deep into this, but just to show you a bit on the technical level how the training of such an embedding model works. What we actually do is we call a skill cloud, which is actually a graph of all linked skills and different representation forms, as we call them. The highlighted skill here for playing means nursing, and all of the linked skills there are different forms of that, misspellings, synonyms, all of these things. And all of these different terms get assigned, so to speak, to the same point in space, the same vector on the other side. So that makes our model robust to such things as misspellings or synonyms and all these things. And once we've transformed this skill cloud, all of these linked skills into these embedding representations, these vector representations, we can do other things to them as well. For example, we can explicitly debias this space by removing certain components from the vectors. We can identify, for example, difference between say male nurse and female nurse. In some languages there are like different words. Don't explicitly have the words male and female, as we do in Dutch, for example, verpleger, verpleegster. It's words for a nurse that have that gendered thing in them. We can explicitly remove that information from the vector representation in order to bias it. I'm always available for questions after the fact if you have ask.
Thank you, Joren, very much. there are already questions for you waiting. We will now go with our third and last speaker of the panel, Dr. Martin Vandenberg. Dr. Martin Vandenberg is an associate professor in the research group of artificial intelligence at the Utrecht University of Applied Science. There, he researches explainable AI with a focus on the financial sector. So I see Professor Martin Vandenberg on screen. Please go on without further.
Thank you very much for introducing me. I'm Martin Vandenberg. I'm associate professor at the University of Applied Sciences in Utrecht. I'm one of the researchers in the group Artificial Intelligence. I'm the head of the research group Explainable AI and conducting research on explainable AI in the financial sector as from 2020. I will tell a bit about the research that we did on explainable AI in the financial sector. On this slide, you can see different studies that we conducted. I will explain the framework that we developed, which is number 1 on this slide, a little bit further. But we also conducted more different research. And following the links, you can find the results on websites of our university. One of the things that we, for example, did is we created a checklist for the implementation of explainable AI, which can be very handy when you start to implement explainable AI for a certain given use case. And the latest research that we will start is to find out how to generate and communicate meaningful explanations to internal users of AI solutions in the financial services industry, because in most cases, you have a human in the loop who has to explain the outcome of an AI solution to customers or clients, and these persons have to understand the working and the explanations of the outcome right away in order to provide explanations to the customers. And that's a rather new research that we just started. But going back to the framework that we developed, which I will explain after I have given the definition of explainable AI that we use, we see explainable AI both as a technical and social capability. The technical capability is the way to open up the black box or to generate an explanation from an AI model or a post hoc XAI tool, for example, job. And the second part, the social capability, is that is the ability to provide an explanation to a given stakeholder, because an explanation needs to be understandable and needs to provide an answer to the questions that the stakeholder has. So it's both a technical and social capability. The framework that we developed is, you can see it on this slide. It consists of types of stakeholders and types of explanations. The type of explanations you can see in the different rows, and these are both types of explanations in the sense of model transparency and process transparency. And the type of stakeholders, you can see the type of stakeholders that we discovered for the use case loan application. So it starts with a loan applicant, financial advisor, etc., and different types of stakeholders in the service provider. And we also recognized different regulators. For example, the Dutch Central Bank, which is the prudential supervisor, the conduct authority, the privacy authority, and the authority consumer and market. All these regulators have information needs regarding explanations. And the different X's in this framework indicate the information demands of types of stakeholders for certain types of explanations. So we developed this framework a couple of years ago together with one of the regulators and together with representatives from the financial sector. And it turns out to be handy to discover what to explain to whom. On the next slide, I have some values and challenges of applying this framework. So the main value of this framework is that it's a tool to find out what to explain to whom. And to me, that's something where you should start when you want to develop explainable AI. Because when there are no stakeholders in need for explanations, it doesn't make sense to delve into explainable AI. And by the way, developers can also be stakeholders that are in need of explanations. So the value of this framework is that it provides insights in different stakeholder perspectives. It creates awareness. It demonstrates that explainable AI is more than just technically opening up the black box. It's a model that helps to abstract from technical solutions, can help in setting priorities and in managing expectations. Yeah, the challenges of this framework when using it in practice are especially that it appears complex and overwhelming, especially to data scientists. They often forget that they have to deal with a lot of stakeholders because they like to develop their AI solution and do not bother that much about the many stakeholders around them. But developing an AI solution is quite complex and requires a stakeholder management perspective. Another challenge is that the framework does not answer the how to communicate explanations. So there is much more behind each cell in the framework than just the X. And another challenge is that that's more a wish. It would be very nice to have also a legislation behind different cells. So what kind of legislation says that you have to come up with this type of explanation for this type of stakeholder? Yeah, I've only a short presentation. So I want to finish my presentation with some lessons learned from our research. First of all, explainability is highly contextual. We researched different use cases in the financial sector, for example, claim handling, fraud detection in claim handling for insurance firms. We investigated credit approval. We investigated arrears management. And all these use cases have different requirements for explainability. And in fact, all the different stakeholders in these use cases have different requirements. So explainability is highly contextual. And another learning is that opening up the black box doesn't mean that stakeholders understand the outcome. In many use cases, at least in the Netherlands, in the financial sector, companies experiment with Sharp. Sharp turns out to be great to provide, for example, the top 5 features that explain a certain outcome. But Sharp cannot be understood by internal stakeholders, such as claim handlers or underwriters. They do not understand that. So we have to find out something that translates these, for example, Sharp values into meaningful information for these stakeholders. The third lesson is that the way explanation should be provided should in fact be a matter of how to design the business process in which AI is used. Because it's something about how to communicate to customers. And that's not something that can be left to, for example, data scientists. It's a business process that has to be developed and designed. And for example, it would be good to involve users, and especially users that communicate to customers, or maybe even customers. And the fourth learning is that explainable AI is not an afterthought. It requires a lot of different aspects that need consideration, and that's why we also created a checklist, which is quite handy, and it tells you that many different choices need to be made in the process of developing explainable AI. So it's also a plea for explainability by design. So it's not an afterthought. That's the end of my presentation. I hope you enjoyed it, and I'm open for questions.
Thank you very much. We enjoyed it, your presentation very much, Professor Vandenberg. I would like to have the panelists to come to the table so they can answer some questions that we already have from the audience. So I will take advantage of being the moderator of the session to pose a first question to any of you, whoever wants to answer, because I mean, I understand that greater transparency can also increase the risk of exploitation of systems. So it could be argued that providing too much information about an AI automated decision-making systems may lead to increased distrust or this to increase risk, okay, due to the complex and often opaque nature of the process. Do you think that there could be something such as too much explanation or too much explainability? How do you envision there must be a balance in this? I don't know if Professor Vandenberg or any of you would like to start.
That's always, yes, there's a need for a balance, and as I think that will be also based on a risk assessment. So there's always a balance to find between when you need explainability and when you don't need explainability. What are the risks? Do you can you afford to take the risk? Indeed, if you have too much explainability, if you have like a security risk or issue or other issues that may arise because you have too much explanation, you need to take into account that in the risk assessment of your system, and then balance the solutions, find a way to understand what will be the impact of that. Just to mention that in cybersecurity, there is always, there have been this approach of security by obfuscation, trying to hide things. And this turned out to not be a good idea, because at the end, there's always a way for malicious actors to get access to the way it works. And for AI, it is a bit the same thing. You can hide things. So you can prevent the model to be explainable or restrain the level of information we give. But bad actors will be able to get access to through proxy models, by virtual engineering the model, to get access to that and to take advantage of that. So if your only layer of defense is hiding how things work, you have the risk, it's not sufficient. So you need to have other ways, other mechanisms to defend your system.
Yeah, I fully agree. I think another important point, and I think that echoes what we saw in Dr. Middelstad's presentation. It should be appropriate for the audience. I think there can be levels of transparency. Some things that have to be transparent to the general public, everyone, and a different level to actual users of a platform, a different level for clients. And in that case, it's not about explicitly hiding details about the system in terms of obfuscation, but in explaining things in a way that makes sense to people. I think that's sometimes a more important consideration than not wanting to divulge trade secrets, for example. And yeah, we see from just reality that if the public has access to a system like this, they will find ways to game it somehow, whether you publish the way that it works or not. So best defense is good design.
Thank you, Joren.
I would like to make a remark.
Yeah, of course. Please go on, Professor.
Yeah, it's a question of finding the right balance. In one of our recent studies, we studied fraud detection of claim handling. insurance claims. And one of the papers that we read in advance also said that the positive effect of providing explanations can be reversed if users perceive an explanation overload. So instead of establishing trust, it could cause distrust. So more explanations can be associated, cannot be associated with trust. So it's not that easy to find the right balance.
Speaking of which, we have a question from the audience. How do you balance the flexibility in trying to interpret similar terms to take into account spelling mistakes or similar terminology with the inaccuracy it might feed into the model, such as how sometimes search engines may give wildly inaccurate results as they try to reconcile that someone who wrote the word cat might have actually meant car or similar? This is the TPO from EUIPO who is asking Cristobal. So I don't know who wants to take the question.
So if I understand correctly, it's about drawing lines, right? Like where do we take the decision to say this sort of term is more similar to this sort of term or something else? I think their context is the most important factor. We have this sort of problem all the time with skills, especially in Dutch, which is a language that tends to cluster things onto words, and where people tend to make spelling mistakes that obscure the meaning. And in that case, yeah, if we want to do it in an automated way, it has to be dependent on the context, like which other terms are mentioned in the same document. What do we expect to be mentioned based on other similar documents? And in some cases, we have to look at how the system works and make a manual decision. Okay, this term is, 99% sure a misspelling of this term, for example. So yeah, there needs to be some human involvement to check the assignments.
There's no other input. I have also a question that is for you, Joren, because there were few questions asking about the explainability budget, and to the participants it was unclear if the right-sided models were more explainable or had a higher or larger explainable budget, or if they were most transparent. If both, maybe you could explain a little bit more on the explainability budget and for example, the location mini model that you showed us before, so to better understand the concept of explainability budget.
Yeah, I'm sorry about that. I realized myself when I sat back down that I didn't explain it fully, but tried to be conscious of time. So the idea behind the explainability budget is, as I showed, that there might be different versions of in our case, mini models. Could be different components of an AI system that have different characteristics. They might have certain power level, whether that's accuracy or some other quality metric that you're tracking. But they might come with a cost as well in terms of explainability and other compliance considerations. So a client might choose to, for example, take the slightly more sophisticated model in one case, but not in the other, to keep the overall characteristics of a model fine. The examples I gave are real world examples. Some clients genuinely prefer the geocoordinate based location model because it's simple and it allows them to visualize to their end users simple circle around the place that's mentioned in a job posting. And if you live inside that circle, you'll be recommended as a good match, for example. So kind of illustrates the decision making and the kind of considerations that clients of us have in configuring models like ours. It's not a black and white thing. There's a nice gray zone where there's room to make strategic choices.
So if I properly understood, what you do is to estimate, let's say, the accuracy or the performance of different models. You estimate also, let's say, the explainability level of each model, and then you, I mean, you have like explainability budget in the sense of, okay, depending on the different models that you apply to a certain solution, you will have a higher or lower explainability. Am I right? Okay. And I think that we are running out of time. We're already we're out of time. So I think that, sorry, yeah. Sorry, dear audience. I don't know if there is any question in the room. I'm very mindful of the time, but if we have time for just one question, maybe.
Just a fast one linking to the one about the balancing in the transparency and security, etc. Coming from experience, because it's more work on dealing with that, is maybe one element that should also can become important is not only the balance, but the fact that the balance is dynamic, as it was one of the presentation was pointing out about the communication. What I mean is the following: pen testing a system for security. If I talk to the developer, I will point out some elements which are important for them. And also a certain depth in a certain way will link it to what is important for them. So project manager, for instance, I will more talk about, for instance, there is a problem with data protection. Your application does not protect the system, the information, the personal data sufficiently. That's more important for a controller or a business owner, etc. in a role. For an authority, if I'm making a system, for instance, with information which could be even classified, actually I will have to document well before I even try to add the system to the people that need to approve it, what I'm going to do it, how I'm going to do it, and if it's a system which is a machine learning system, very difficult to make people accept is machine learning, not AI. I know the problem by experience. Then it will be more complicated exactly because then you need to be able to explain something which you may yourself need to investigate how it works so that you can explain it to someone who might not be even a specialist. So you have to explain it in ways which are more understandable for them. And then you have a normal person, if you have another application, to which is not the business owner, is not the project manager, it's not the developer. They don't even want to understand or can understand too much the details of whether the personal data is well protected, but they want to understand how the decision, for instance, whether I will get a loan or not, has been made, why I was refused. Does it make sense I was refused? See what I mean? So there may be even I think one element would be also that the balance may change for the same thing, depending on the context and to whom you have to answer.
Some input, because you all just brought the cases in which I am involved the most in terms of credit scoring and medical diagnosis and recruiting as well. One of the elements of transparency in which I'm working a lot now, and I would love to hear your input, if not now, later, it's all right, is in terms of where, sorry, I just lost my voice last week, so I'll do my best. In terms of explaining the right to ask for human intervention when that's mandatory or applied anyway. And this, what the Professor Vandenberg, sorry, said before in terms of it's very much impacted by the process and the design of the process, because we are thinking about the scope of that human intervention. For medical diagnosis, could be just the professional reviewing the case, but for credit scoring, we're struggling a little bit more, and I am considering whether we should wider the scope a little bit more in terms not only for someone to review the case, but also someone reviewing the algorithms if there are some biases found from that case raised by an individual. So, and I'd like to know your experience inputs on your cases as well.
Thank you. So I don't know, maybe
Can,
Professor Berg, because you were directly, Martin?
Yes, I can respond to the question. Yeah, from my research in the Dutch financial sector, I know that in most high-risk use cases that we researched, there is always a human in the loop that can provide explanations to consumers or clients or people who have to who want to ask questions to the financial service provider. So there's, in fact, there's always a human in the loop, and the companies that we researched are very cautious in implementing complex AI models. They have a strong emphasis on having these models explainable, at least to the internal users and also to the clients. But the clients are mostly connected via the humans in the loop, so the internal users of the financial service providers that provide the clients with answers to their questions. So there's no direct interaction in most risk use cases between the client and the financial service provider.
Thank you. I don't know if you want to react to the previous question or.
Maybe I just wanted to comment that this is where Explainable AI will help to support the requirements, and it will support human oversight, it will support other requirements, but in itself, there will not be a need to have explainable AI or to make a system explainable, but to make sure that human oversight requirement is fulfilled. And here XAI can help. And the way it will help will be based on practices, based on standards, based on the implementation actually will be or will not be based on XAI. So this is where I like to maybe turn down a bit the wall of XAI. There might be cases where XAI is not the right solution to achieve human oversight because the system is too complex, and then there's a need to have other tools.
Okay, thank you very much. We can continue now. We will have a shortened 10 minutes coffee break.